Hello and welcome all to this part 3 of the hands-on computer vision tutorial. In the previous section, or part 2 of this tutorial, we have seen how to write code to detect indoor objects by using Detectron 2, which uses an instant segmentation model for object detection. We have seen all the steps from installing the libraries, registering the dataset, visualizing the dataset, training the model, loading the model, and using the model to make inference. Now, in this section, I will walk you through the results and how we test our model with certain boundary conditions. How our model performed on the test dataset, the dataset which the model has never seen before. How the model predicted the classes on this never seen dataset, and how can we calculate the performance of the model. But let us first talk about the dataset, the test dataset a little bit. So as we have already seen how I created my custom dataset by taking random images of some indoor items or downloading the images from the internet. So this way, I have gathered around 630 images in total. Then I have taken the 80% of the images, which constitutes around 500 of them for training, and the remaining images for testing. Keep in mind that we do not have to annotate the test dataset using label me, as we did earlier with the training dataset. Test dataset needs to be fresh, that the model has never seen before. Now, coming back to the results, I have taken images with different objects inside it and let the model predict the different classes, and this is how the model predicted all the objects in the images. As I have already mentioned that we are doing image segmentation to detect objects, so the model will not only draw the bounding boxes across the images, but also mask them like this to provide the shape of the objects as well. Now moving on to the testing. Testing plays a crucial role to decide on the performance of any machine learning model. It is not just about the testing itself, but the quality of the testing and the comprehensiveness of the testing. I wanted to test my model holistically to know all the strengths and limitations of my model before I can say that it is now production ready. So I have developed metrics on my testing images with different image parameters like image size, object orientation, object color, object size. For every metric, I kept varying one parameter and keeping all the other parameters constant. So in this matrix, you can see that the object iron with the file name of i72.jpg, I am keeping the image size, the object orientation, the object color constant, and just varying the object size. So at first, I kept the object size to 500 by 500 pixels and let the model predict, and the model was able to predict with the 92% accuracy for this particular object. Then I kept reducing my pixels or the object size from 500, then I moved it to 300 by 300, and the model was able to predict with an accuracy of 91. Then further reducing the image, the model predicted a little less at 86% confidence score. And then when I further reduce the image, and you can just imagine that how 75 by 75 image would look like, it's going to be very, very small. So the model was not able to predict at all. Next up, I have kept the image size, color object, the object pixels here constant, and just varying the object orientation. So I have an image, I tilted the image 90 degrees and further to 180 degrees. For a 90 degrees tilted image, the predicted accuracy was 65%. And when I completely put the image upside down, which is 180 degrees, the model was not able to predict that. Similarly, keeping all the other parameters constant, and this time just changing the object color. Previously, it was like the colored image, and then I changed the color from RGB to grayscale, and I saw that the model was able to predict with an accuracy of 93%. So this is just for one image, and we have to do this for significant amount of images, and then we can take the average, and then we can conclude. So what we can conclude from this particular matrix, that based upon the information of this matrix, we can conclude that our model can perform well for the images with sizes 150 by 150 pixels and above. The images should not be upside down, and the color of the image, whether it is an RGB or grayscale, doesn't make a difference. You have to make similar matrices for significant images and different objects and take the average of them before you conclude the strengths and limitations of your model. Here I have taken just one example for just one image to show you that how this rigorous testing can be done. Then moving forward to the performance evaluation, here we are talking about the training efficiency. And next up, we are definitely going to be talking about the testing accuracy as well. So for the training accuracy, we have 4 matrices, namely class accuracy, total loss, false negative, and the learning rate. These graphs are generated using the TensorBoard. These can be generated by introducing the validation dataset. Earlier video in the code walkthrough, I have used train and test dataset for training and testing. However, the performance evaluation, you need to have a validation dataset. I have added a comment in the code in the last section on how to introduce a validation dataset. And the validation dataset itself can be found in my Google Drive. And all the links are going to be present in the description below. So on the x-axis, we have cycles or iterations, which we set in the code to 4,000. So, and the y-axis indicates the accuracy in percentage, or it's, then we can just multiply by 100 to get the percentages of it. So let's see when the model is in the training stages. In the first cycle, the model got trained of just for the first cycle, and then it predicts something, and the prediction percentage was less than 1%, because I already gave you the idea that these neural networks are inspired by human brain. So as the human brain works, that the human brain is also not able to learn anything just by seeing it for the first time. You need to do repetitive iterations to get that thing consolidated in your mind. So starting off with on the 0th cycle, the accuracy was very less. And as soon as the cycles kept on increasing, which means that you're training on the same images time and again, so the model starts to predict with a class accuracy of around 99%. Here, the total loss was obviously very high, because how this total loss is generated, it's the difference between the actual image, the actual object, and the predicted object. So at the first cycle, our model was not able to predict that thing correctly. So it started off with a very high total loss. And then as soon as the cycles kept increasing, our accuracy has gone up. So definitely the loss kept on decreasing and decreasing. The accuracy and the total loss are always measured side by side, because as soon as the loss starts to decrease, the accuracy will definitely tend to increase. So next up is the false positive, means how much objects did the model predict wrong. For example, if the object was lamp, the model predicted it a cup. And it can also be seen that the iterations increased, the rate of, as the iterations increased, the rate of predicting wrong values decreased. And the last is the learning rate, which is set in the code to 0.00025. Learning rate means at what speed the model is learning. So a high speed is also not good, as if you try to learn everything in a very fast paced, it's highly likely that you are going to forget it in near time. And neither it's a good idea to have a very low speed. Otherwise, it would take very long time for you to learn something. So all these neural networks are inspired by our brain. So how the brain works is actually the configuration of these neural networks. So the value 0.00025 is a good one. Neither it's very fast nor it's very slow. It's pretty reasonable. So until now, we have seen the training accuracy. Now we will see the testing accuracy. First question is what parameter or criteria is used to measure a computer vision or instance segmentation model accuracy. So typically models are evaluated according to COCO evaluation criteria. The average accuracy or average precision, which is the abbreviation for AP, is used to evaluate the performance of the model. AP 50 here and AP 75 here means the actual object or the bounding boxes on actual object and the bounding boxes on the predicted object coincide around 50% or 75%. So the actual object has the bounding boxes somewhere here and the predicted object has been somewhere here. And if they coincide to around 50%, then it's going to be AP 50. Or if it's like more than 50%, like 75% coinciding, then it's going to be AP 75. So 92% and 81% are pretty good numbers when it comes to average precision. More details about how this accuracy is calculated, I will drop a link in the description for a quick read. This one is kind of more explanatory because here we see that the accuracy for individual classes. And we can see that the accuracy for chair, clock, kettle, 86%, 90%, for lamp it's 74%, then for cup it's 93%, for laptop it's 82%. But if we see closely that the accuracy for fan is just 24%. Why is that? I kept the images for fan less intentionally so that we can see the difference between the accuracies of the other objects and we can discuss how this thing can be improved. So for all the other objects, I think the average number of images to train the data was greater than 100. It was somewhere around 100 and 110 images for every class. But for fan, it's around 24, 25 images just. So as a kind of a follow-up exercise, you can include more data on any of the objects and see if the accuracy increases. So that's all from the computer vision tutorial. I hope that this tutorial was useful and will enable you to train your own image segmentation models and apply it to the other use cases. Please give this a comment, like, and subscribe to this YouTube channel. Thank you and see you in the later videos.